And it looks like we've
All
got
right.
Lehman who's connecting right now, which is
No, I'm
awesome.
here.
Hey,
Yeah.
Lehman.
Hey. I heard Zenobia. It sounds like we're all here.
The crew is here.
Hello,
All right.
hello.
Hello. I see people waving. Hi. Hi. Sorry for the technical difficulties.
Lehman, welcome. I believe this is your first Twitter Spaces.
My first Twitter Spaces. Good to be here.
So we are, if you all can hear me okay, if someone can give a thumbs up, I will go ahead and get started. I do know that Spaces can be buggy, but we have had some requests to do this and to try it out, and I think there's a great audience here. So we're going to give it our best shot here, and if anybody at any point cannot hear me, let me know somehow, wave or something else. And I do want to give a shout out to the person joining who has the number 10 Argentina jersey on there. My sons were very happy with last night's nail biter of a game. All right, Lehman, we have so much to get through, and as always, so little time. So I'm going to jump right in. As I mentioned, these are some of the questions that we did not get to. We appreciate everybody submitting them for the town hall, so we wanted to try to carve out a little bit of time to address some of the additional ones. There were a lot of technical questions this time. Lehman, the first one I'll start with is, can the native layer do everything that a smart contract can do? And if there are limitations, what are they?
Sure. So yeah, the native layer, by this I assume you mean the consensus service. It can do everything a smart contract does. The consensus service runs much faster, but you do need to have, for at least some applications, an AppNet. So that's the trade-off. If you do it with the consensus service, you can do everything a smart contract does, but you need to stand up some computers, if it's the kind of thing where you want them to be coming to an agreement and maintain their own state. And so it's a little bit more work. Now, the good news is that you can use any of the systems out there like Hyperledger Fabric or EA or whatever, and then just have a plugin at the bottom that connects it to this service, in which case it's just sort of flipping a switch, and now suddenly you have the trust of Hedera. But you do have to stand it up. On the other hand, with a smart contract, you have a smart contract, you have Solidity, you run it on the network, and it runs at the speed and cost of a Solidity contract, which is a lot lower cost than other ledgers, but it's still slower. But you don't have to stand up this network, and so maybe it's easier for you. Also, you do have to use Solidity. If you're using the consensus service, you can use whatever language you want, and that makes it more convenient too. So there's trade-offs. There's ideal times to do each of them. But in a lot of ways, the consensus service is better because it's faster. You're at the native layer rather than at a higher layer in the stack.
All right. Thanks, Lehman. Related, what are your plans? How do you become more attractive for migration of Dapps from other platforms?
Sure. So first of all, if you have something in Ethereum, you can just move it right over. Sorry, not Ethereum, in Solidity, like would run on Ethereum. If you have a Solidity smart contract, you can just run it directly. If your smart contract though is an ERC20 or 721, you might want to improve that slightly. And you might want to actually create a token using the Hedera token service. Again, tokens are at the native layer, and so they're much faster, but you can also use a smart contract for your tokens. But you're better off just creating the tokens at the native layer, and then it's much faster. So you can do that. If you want to know how to do it, we have a number of communities of people working on this. We have Discord people discussing it. We have code written and that we give out. We have developer evangelists that will talk with people and help people. We have a community that is building SDKs and building other tools to help. We have people building things like wallet, lots of source code released. We built a wallet and released it open source. Now the community is taking that over. We've built a bunch of SDKs and released them open source, but now the community is making SDKs in other languages. And so there's a huge community here and lots of resources to help you get started, documents that talk about how to get started on developing with Hedera. But if it's just a smart contract you want to move over, you just move it over. But there's a big community here to help you do more interesting things than that. It's wonderful to see that community.
There is indeed, and they are so creative and have thought of so many things. And I think they just bring such a great set of experiences and background. I'm always just amazed at the kinds of things that people are building on top of the platform.
Mm-hmm. It is amazing. I didn't even mention hackathons. I get to see even more of those in the hackathons. You guys are amazing, seriously.
All right, Lehman, the next question is we have something on the roadmap on automated congestion pricing. Can you explain a bit about how this will work, and will network fees increase depending on network usage, and how will they be calculated?
Oh, yeah. So this is just an emergency thing. So this is not something that would trigger in normal use. If the number of transactions per second on the network doubles, it doesn't mean your prices double. Your prices don't change at all. Right now, we have the network throttled down to only 10,000 transactions per second. If it gets really close to that limit, we're nowhere close to 10,000 transactions a second, but if we get very close to that limit, then congestion pricing kicks in and the prices go up. And if we didn't do the congestion pricing, then we'd probably just hit the limit and then you wouldn't be able to submit a transaction. So instead the prices go up and then you can submit them, but they're more expensive. But other than that emergency scenario, there is no change in the pricing at all. The pricing is in US dollars. It's consistent. Even as the price of the HBAR goes up and down, the prices are consistent. In the council changes prices when they think it needs to be changed. And in the last year and a half since OA, I don't think we've had a single change. I think all we've done is added new features and had to pick prices for the new features, new services. But I don't think we've ever even changed the prices. So yeah, right now, if you see 50 transactions per second, we have a price. If it goes to 100, it'll be the same price. If it goes to 1,000, it'll be the same price. If it goes to 2,000, it'll be the same price. It's only when you get up to 9,000 something, then it starts getting more expensive. That's all that is.
All right. Thanks for clarifying that one, Lehman. Okay, we have a question on HCS. Can HCS be used for reconciliation and settlement process between financial entities without compromising the security aspects of financial secrecy or confidentiality?
Yes. So this is a fascinating use of HCS. HCS, the Hedera Consensus Service, is a way that you can send a message through Hedera, and the whole world sees it. You know that everyone is seeing the exact same things, and it is guaranteed that the consensus was that it was a certain point in time and has a timestamp on it. And the mirror nodes all have it, so people can even get it from the mirror nodes. There's this immutable record kept forever, and that immutable record is cryptographically protected. You have actual signatures, digital signatures from the network saying this was our consensus, and we believe that this message flowed through us at this time and was visible to the world. Now, if you want to do a transaction that requires privacy, so suppose you and I are doing this transaction, some kind of a financial transaction, and I'm required by the contract to send you some information, and then you have to do something and maybe send me some information, and we don't want the world to be spying on us. Well, what do? Well, we can encrypt all those messages that are flowing through HCS. And so we have all those messages flowing back and forth, but all the world sees is ones and zeros, and we can use an anonymous account to do it, and nobody even knows who's doing this transaction. We just fully do it. Well, what good is that? But then if I were evil and I lied and I said, hey, you were supposed to send me something and you never sent it, therefore I'm off the hook, I don't have to follow this contract. You could take those encrypted messages to a court, give them the key to let them decrypt it so the court could actually read the message and say, look, this message I really did send out. And maybe Lehman didn't decide to read his mail, but we know for sure that it was available to Lehman because it was available to the whole world through Hedera on all the mirror nodes and on Hedera itself. He could have read it and he knew to expect it. And so it is his own fault if he didn't read it. I sent him the information and here's the timestamp on it. And here's the cryptographic signatures from the whole network. This is Hedera itself standing by the fact that I told this to Lehman. And you can prove it into a court. But if you're not doing that, if you're talking to some person on the street, they will have no idea what you have total privacy. And the whole thing happens in a few seconds, so you have incredible speed. And so it gives you, and they're very cheap. It's a tenth of a cent to send it. And you don't even have to send your entire gigantic document. You can just send a hash of it, and you can encrypt your hash. And so it's extremely fast and cheap, and easy to do, but it gives you this perfect cryptographic record to prove that you've done it if you ever need that proof in a court. Or even if I just forgot about it and you wanted to remind me later, no, you really did do it. Look, here's proof of it. And you can have total privacy. You can encrypt the whole thing. So that's a very cool usage of HCS. And I don't think I've heard of a lot of people doing that yet, but I expect that as our industry takes over the world, you're going to see more and more uses just like that.
Very cool. Thanks, Lehman.
Hello? Can you hear me?
I can hear you,
Okay.
Lehman. It looks like I might have been cut out.
Good.
My apologies. The connection's it's a little bit dicey here, but okay. So, the next question comes from the fact that we've talked about how we have nodes on every continent except Antarctica. Does the end user distance from the node matter for nodes when they are actively participating If you are in a specific region, does that have any impact on consensus?
Okay, so not exactly, not really. So here's how it impacts it. We could ask for a given node, if you are a client sending your transaction to that node, maybe it's really far away from you. How does that affect how long it takes you to reach consensus and how long it takes you to get finality? And then we could also ask the node you're talking to, if it's really far away from everybody else, how does that affect it? So here's the answer. You will have a slight delay when you go to that node, and you can pretty much get to any computer on Earth in less than a second. So in a fraction of a second, often a pretty small fraction of a second. If you use Elon Musk's system, he's saying 20 milliseconds. So, a 50th of a second. That's a really tiny fraction of a second, and he claims it'll even get better. So, but every place on Earth, I have never any nodes being more than a second to them. Maybe if you're behind a country that has a big firewall that really slows things down, you would. But usually you get to it very, very fast. And so what you do is you send your transaction to that node, and there's this fraction of a second before it gets it. Then that node has to gossip it to the rest of the network, and that happens extremely fast because that node gives it to another node, and now 2 of them have it. And then they each give it to 2 other nodes, and now 4 of them have it, then 8, then 16, then 32, then 64, and it explodes exponentially. So if in that fast process, one node, like the starting node, was an extra even half of a second farther away, which is a huge amount, it has basically no effect. It just delayed half a second getting into the big group of fast nodes, but once it's there, it spreads it like wildfire through them. And so it's extremely fast. And so your ultimate finality will be several seconds. And the choice of which node you went to is just a fraction of a second. Now that's if you're on Earth. If you're on the moon, it adds another 1.5 seconds for that first hop. If you're on Mars, it could add 45 minutes. Depends on where Mars is compared to Earth. And we'll have that in the future, I think. I think you'll have people on Mars sending messages to the network, and there'll be a 45-minute latency, and you just accept that. But the cool thing is once it reaches one of the nodes, it spreads to all the others really fast, and then they get consensus. And most of the time is all of them talking to each other to reach consensus. And so people who submitted through different nodes end up getting consensus at the same time, except for that very tiny delay at the very beginning, which would add up to less than a second. And so that's kind of how it works. What is bad is if everybody always sends to the same node, then of course you might just get slowed down because there's a lot of people using that node. And so what you want to do is pick random nodes. And so if you're writing software, I would always recommend pick random nodes, have every transaction go to a random node. If you notice that a node is down, maybe just don't send to that node again for a few hours. But just pick random nodes, and then everything gets spread out randomly, and you'll find that it works really well.
Thanks, Lehman. All right, anyone who needs their transactions to calculate the distance from the moon or to be on the moon, work that into your applications, please. Okay, Lehman, this is sort of a a nomenclature question. The average observer hears the word transactions in the context of the cryptosphere and thinks of things that are 1.2, I think 1.3 billion transactions now means 1.2 billion cups of coffee were paid for. While that sounds like a delicious amount of coffee, do you think we would be better suited to talk about Hedera in terms of processing IT events instead? And why or why not?
Terminology is always a problem. And in our industry, we even have contradictory definitions of terms. Is a hard fork a good thing or a bad thing? Well, if it splits the network, it's a bad thing. But every single time you have software, that's a hard fork. That's a good. We have lots of terms that are used different ways. Some people use blockchain to refer to a DLT in general. Some people use it just to refer to a blank chain of blocks. So is Hedera a blockchain? Different ways of defining it. Same thing with transactions. The standard term in this field is, in our community, is transactions. Is that clear to an end user, a random person who's never heard of a blockchain before, never heard of a ledger? I don't know. Maybe that's misleading. Your transaction may not be buying a service from Starbucks, but it is buying a service from the ledger itself. And so it really is a transaction in a very real sense. It's not a bad word. We could try to make up other terms like IT events, but I'm not sure the average user knows what an IT event is. I'm not sure that I do. Every alternative term we make up, you'll have different definitions for it or different ways of understanding it. I think that the best thing for us to do is to just help people understand. I mean, talk them through it, give them explanations, try to explain it in simple language for them. And we're not the only field that has confusing terms. Like in physics, a black hole can be white, can be bright white while it's exploding, while it's evaporating at the end. Cherenkov radiation is when something that can't go faster than light goes faster than light. Light, photons are massless, yet they have relativistic mass. All these words actually sound contradictory. And this is true in every field. You have technical terms and they sound contradictory. We should definitely be doing, I love what you're thinking here, is let's make things as easy for the lay people to understand as possible. And I think we should do that. And so anytime we have a chance to explain things to new people, we should do so in ways that are as easy for them to understand as possible. And if you're talking to someone who works in an industry where IT event is a term they're really familiar with, then you should use that when you're explaining it to them. I think it's on all of us to try to educate the best we can.
Yep. Know your audience,
Yeah.
right? All right. This next one, given how much cyber criminals are in the news recently, how much havoc they have wreaked on the traditional internet, Lehman, as you thought about the security of the network, what kinds of bad actors did you have in mind when establishing the concepts of hash graph security? And are they individuals, groups, companies, nation states, all of the above? Any insight into your thinking there?
Yes. Are we thinking about individuals, groups, companies, or countries? Yes, absolutely. No, seriously. The whole,
Yes.
everything we do starts with worrying about security. Anytime we talk about a new feature, the first thing we say is, what are the different attacks that can be done on it? And if we can't find a way to harden it against all the attacks we can think of, we will not do the feature. And we have made choices purely based on attacks that we've been able to think of. Everything we've done, the hash graph algorithm itself was started by the math question of, could you make something resilient to certain types of attacks? Could it be ABFT, not just BFT, and not just hope for the best? And that was saying, specifically, when you say A in ABFT, asynchronous Byzantine fault tolerant, what you're saying is that I assume some of the nodes in the network are attackers. They're going to be malicious. They're going to lie when they send out messages. They're going to try to flood somebody with messages. They're going to try to start a conversation and then never end it and see if that ties them up forever. They're going to do everything malicious they can think of to hurt you when they're talking to you. And then we assume that the attacker also controls the internet. So the A in ABFT means maybe you're in a country that has a firewall around it, and you're talking to someone in a country that doesn't have a firewall around it, so there's a firewall between the two of you. What if the firewall stops things? And you can say, well, if it completely cuts off communication, then we should survive as long as if only a few of us go down. But what if it's more than that? What if it is trying to make some of the packets slow and some fast and change the order? And what if it's doing it in a very malicious way? And what if they own one of the computers in the network, and so they know everything the network's doing, and they can very maliciously craft their attack? This is the exact kind of thing we're looking at. And we also have to worry about things like DDoS attacks. It is possible for an attacker to do what's called a distributed denial of service attack, a DDoS attack. And what they do is they go in to hack into little computers around the world. And when I say computers, I mean things like printers or security cameras or baby monitors. Everything in the world has a computer these days. They hack into a whole bunch of them, and then they make them all send messages at the same time to one computer on the internet. And they just flood it with so many packets that it can't talk. It can't hear what legitimate people are saying, and it can't talk out to legitimate people because you have to have some handshakes as you're talking. So it is just shut down, essentially, for as long as the attack continues. Now, of course, if an attacker shuts down every node in your network, then your network shuts down. But you should never have them shutting you down if they only attack one or two nodes. This is why it's such a big deal that we don't have leaders. And this was from the very beginning why we didn't even consider having leaders, where one node is the leader that puts everything in order, and we take turns being leaders. There are lots of systems that do this, and they say, hey, we're really fast. Well, of course you're fast. Everyone sends their message to the leader, and the leader sends back out with the right order. Done. The problem is the attackers could do DDoS attacks on the leader, which would shut down the network. And you could say, well, we take turns, wait a few seconds or wait a fraction of a second, we'll have a new leader. Yeah, but remember, we're taking into account attackers who own one of the nodes in the network. We're assuming that, which means they know who the leader is, and they can just keep redirecting the attack and follow the leader. And so we have always been worried about these things. And that was just in the hash graph algorithm itself that we were worried about these things. We were also worried when we designed the council for what kinds of attacks could happen. We said, what if a government tries to shut it down? If we have all of our leadership in one country, or if we have most of our nodes or most of our hashing power or whatever in one country, then the leadership of that country could be nice and just kick you out of the country, or they could be not nice and take over and cause the network to act maliciously and then completely destroy the network because they have most of the nodes. So we said we wanted it to be in different countries around the world. And so we have our nodes and our council, our government people are spread around the world. And we wanted transparency because we are worried about malicious people doing things in smoke-filled rooms that you don't know about. So what we did is we created a council that publishes all of its minutes. It's together every other month, publishes the minutes. So the whole world sees what they're doing. And we were worried about, could you bribe one of these guys to do something bad? So we only go with very large players, big companies or big universities, top 10 university in the world, that kind of thing. So that it becomes very hard to bribe them to do it. And we worried about becoming ossified. What's going to happen? This is mining for the 100 years. From the beginning, we were worried about even attacks that might take a decade. And so from the very beginning, we said it could become this small little cabal that becomes very ingrained and never has all the power. And so we said, no, we're going to have term limits. And so they will continually be turnover in the council, and we'll have new members. And so we even have diversification, decentralization in time. And that was because of various attacks, the different attacks I've been talking about. We were worried about attacking from, say, one of the governors or one of the nodes that are or one of the governors, I should say, that are not caring about the reputation. They just want to make a quick buck. But the big organizations we have are all caring a lot about their reputation. And it'd be very hard to bribe them or for them to do something malicious that gets out, and they'd be willing to do it. And so we've dealt with that attack. Or even if all of the organizations are in the same industry, they were all schools, they're all telecommunications, they're all banks, them colluding because they're all in the same industry. And so we had them in different industries. So everything about the algorithm, everything about the governance, everything about the new features we're adding, the very first thing we start with is what are all the different attacks? And we say nothing is ruled out. Every kind of attack, every kind of hacking is what we think about.
Yeah, Lehman, I know you and Mance and I have all lived in the security world for a long time. And so, that is front and center in everything. And I think in some ways, maybe we could have an entire session on that, but that might be more depressing and realistic than than we want to tackle.
Oh, well.
All right. We are going to try to get through as many of these as we can. Okay. The internet may be one of the greatest models we have of a decentralized platform. And, we have talked at Hedera a lot about being the trust layer of the internet. Lehman, can you talk about why you think the existing internet was so successful and how perhaps some of the lessons from that have informed our strategy for adoption?
Yes. So fundamentally, the internet was about being able to share information. Share it with people that you know and also share it with strangers. So, website is sharing information out to the strangers, and email is sharing with someone you know. The whole purpose of the internet was to make sure that information could be shared. And this was a pent-up need that the world maybe didn't even realize it had. And the effects of the internet on society and on business and on every aspect of our culture is enormous. It's hard to even imagine. We're all glued to our phones right now. If your phone didn't have an internet connection, nobody would be glued to their phone. Okay, maybe the internet's bad. But this is the case, right? I'm glued to my phone all day because it connects me to the world through the internet in ways that would have happened otherwise. But it is clear that the problem it solved, it only half solved. Yes, I can get information out, but how do you know I'm getting the same information to two different people? Yes, I can put information on a website where everyone can see it, but how do you know that information is going to change over time in a legal way? If you have a bank account, you want your bank account to change over time as you send people money, but you want to make sure that you can only send the money if it's you doing the sending. And so you want an immutable record of everything that's happened, but you want the current state to only change according to the rules. The point of a smart contract is that its state only changes according to the rules of the language and of the smart contract you've written. And everybody can see the smart contract and know it. And the same thing is true when you send tokens. You make sure you have the token before you can send it. And if you try to send it to two different people, it only goes to one of them. You don't have double spins. And so the internet was all about sharing information, but it wasn't about trusting the information. And the internet revolution really was just half the revolution. The other half, that there is even more unimaginable demand for in the world, is that, yeah, we can share information, but can we trust the information? And so this is what distributed ledger technologies in general, blockchains, ledgers in general, are doing. And this is what Hedera really wants to do. And we believe that we really do have a world that needs the highest level of security, ABFT, but also needs incredible speed, tens of thousands a second, and also needs extremely low pricing. And if you can do that, and then if you can have good governance and transparent governance, remember, it's all about trust. where people know who the governors are, they know everything about them, they know that they have a reputation to protect, they see their discussions, their minutes are published. If you can have this kind of security and transparency, this is what the world needs to get the second half of this information revolution. You need an internet to get the information out, and you need a ledger to make sure that it is trustworthy. Also, as a side note, I should point out that the key of the internet, internet means internetwork. The idea was we had a whole bunch of computer networks, and they used all sorts of different technologies, token ring and other weird things. And the bright idea was, well, we should connect them to each other. So the internet wasn't a new network. The internet was a network of networks. It was an internetwork. And I think we'll see a lot of good things coming out of ledgers connecting to each other, having bridges between ledgers so that you can move tokens and other things between ledgers. And we'll see more and more of this over time too. And it will help the industry the same way the internet, being an internetwork, helped that industry. But this is where we see ourselves going. I do think that this is just going to change the world. And everything we've done with Hedera is to make it a 100-year company that can be a utility for the whole planet to help provide this need. And this is where we are.
Yep. As you said on the town hall, Lehman, rising tide, lifts all boats. And the more we are interconnected with these systems, I think the greater value we're going to see out of them. Mm-hmm. Our next question, we got a few times this month, and I don't think we'd ever had it before. What is a fake stake attack, and is Hedera safe from these kinds of attacks?
Oh, I love it. I have all these technical questions. I'm so glad we're doing this because we didn't have time in our town hall to cover all these technical questions. This is so good. So yeah, let's talk about fake stake attack. No, it doesn't apply to ledgers like Hedera at all. So here's what it is. Hedera, of course, as a proof of stake system from the beginning, and we store balances in state. So if you want to know how many HBARs you have in your account, you look at it, and there's this universal state that all the nodes agree to, and you can get it from a mirror node, and there's cryptographic proofs that the mirror node has to know it's real, and it's very simple. It is a number that is stored on all the computers in the network. That number is how many HBARs you have. Or if you have a token, how many tokens you have, and what kinds they are, all that stuff. If you have a smart contract, it's the state of the smart contract. However, in some of these older systems that were based on proof of work, they were also often based on unspent transactions, which means you don't exactly have a current state of all the balances. You have these older things that are buried down in the stack, in the chain of blocks. And you didn't have proof of stake, you had proof of work, but there's reasons to be greener and to try to make it proof of stake. That's better. And there have been recent attacks on some of those attempts to take an old proof of work system and make it proof of stake, where that are based on unspent transactions, that end up being that the attacker does just the right things. They can do resource exhaustion attacks. And so it is just too hard for you to keep track of the stake and be using it and storing it and thinking about it. And that makes it difficult. It slows you down, or it overwhelms you for consumption. So for something like Hedera, it's just not an issue. A node has stake. The stake is HBARs in an account. Right now, it's stored in a slightly different way. You can look at how that's stored. At some point, it will be actually the HBARs in an account or a bunch of accounts that give the stake for that node. And all the nodes in the network just know the balances. If you ask it for your balance, you get the answer instantly. There's no attack that would cause it to be extra hard or extra slow or use extra memory to know your balance. Your balance is just a number, and every computer has that number. And so knowing what your stake is just trivial. And so this kind of an attack doesn't work. I don't think it works on any of the ledgers that were built proof of stake from the beginning and that store actual balances for accounts. I think it's this attempt to make the legacy systems work better. So that's a very technical question. And I think it's just really cool that people are really getting into these technical things. That's cool.
All right. Well, we're going to keep that train going. Okay. What is the motivation for wipe transaction and freeze account transaction? And what are their intended uses in different scenarios? And I think this person is asking in the case of CBDCs, and when you think about, political control, control by authorities, is it possible to avoid usage by some of those different parties in a neutral technology, and I don't know what this last part means, and an API call?
I'm not sure, but I understand the question. So this is an excellent question. When you create a token, the person who created the token, what kind of power should they have over it? And the answer is they should be able to choose how much power they have over it. If you write a smart contract that has tokens, like an ERC20, you have the ability to modify that smart contract when you write it to give you infinite power, to steal tokens from people, to freeze their tokens, to turn off the whole system, whatever. You have the ability to put all sorts of backdoor powers for yourself in the smart contract. And in some sense, that's fine as long as everybody knows about it. So for example, if I were to have tokens that I give my friends that let them get into my house, right? If I had an electronic door lock and somehow tokens let you get in, then of course I should maintain all the power. I should have the ability to revoke a token from a friend. I should be able to have the ability to freeze their account so they can't use the token to get into my house. No problem. On the other hand, if you're building a CBDC, you probably don't want to have the ability to do those things. Or maybe you do, but some people would prefer a country that doesn't. If you're just creating a typical ERC20 and ERC 721 kind of thing, you're just creating a token, usually you're going to find that it's most useful if you don't give yourself infinite power over it. And so what does Hedera do? We give you the ability when you create the token to set it up any way you want, in a way that's visible to the world, you can't keep it secret, and you can't change your mind later. If you want to, you can create a token with our token service that has admin keys that let you have all sorts of powers. You are the king of the universe. Or if you want to, you could set it up with joint keys where there's a whole bunch of different people that everyone knows and trusts not to collude, and the majority of them have to agree before something bad happens, before they delete a token or freeze an account or whatever. And that way you can trust it maybe. Or you could create your token with no admin keys. And in that case, nobody has this power, and guaranteed no one ever will have this power. If you don't put admin keys on the account, create it, it has a guarantee to its users they're never going to, it's never going to have admin keys. You can't add them later because adding them would require a signature by the admin key. If there is no admin key, you can't do it. It's kind of a catch-22 there. And so the point is, if you're going to tokenize $1 million painting and sell me that token, I'm going to pay $1 million for it. You want, when you're buying this painting, you want to know that they're not going to be able to go out and reach out and grab it back from you for no reason. And so nobody would ever buy an NFT if it had these kinds of admin keys on it. And it's totally transparent. They can't trick you. And so that's the idea. Just like a smart contract gives you infinite power when you create it. You could do something evil, you could do something not evil, but it's then transparent to the world. And if they see you've done something evil, presumably they're going to not use your token. And we have the same thing in our token service. The goal is, actually there's lots of standards that we're having features from those standards. The goal is that for some tokens, you want to give the creator lots of power. For other tokens, you don't. And the important thing is that it's clear to the users, and that if it has been created from the beginning to be a token that has no king ruling over it, then it could never in the future suddenly gain a king. And that's what we do. So that's been the philosophy guiding how we've done our HTS, our token service.
Thanks, Lehman. I know I always enjoy hearing a little bit more of the background too, not just the answer, but also why. So that's helpful. Okay, we've talked a little bit about being in outer space. The next question is, does time dilation, say from a potential satellite node, have any effect on Hashgraph's ability to come to consensus, or perhaps the order of timestamped transactions?
Oh, I love this. I love these technical questions. Okay, so if you're just talking about ping times, actually, a satellite in orbit using Starlink is going to be faster than the nodes we have on the ground right now. That's cool. But maybe you actually meant time dilation. I love that. So you guys know, according to general relativity, if you have a satellite up in orbit, it is going to moving fast around the Earth. And anytime you move fast, your clock slows down. But at the same time, it's high above the Earth, where gravity is weaker. And anytime you move to a spot where gravity is weaker, your clock speeds up. And in fact, the GPS satellites, they take into account both of those two effects. General relativity makes it go slower, and it makes it go faster. The part about going slower is actually special relativity, but it's also in general relativity. Does that have any effect on the clocks running at different speeds? And the answer is no, not at all. We will always come to consensus, regardless of how bad your clocks are. And we expect an honest node to do its best to sort of keep in sync, more or less. But if we have a bunch of dishonest nodes that are 1 million years out, I mean, literally 1 million years out, yes. And if the honest nodes only, update their clock occasionally, and you have time dilation in orbit and you're not compensating for it, maybe you get a few seconds off every day, it doesn't matter. We'll still come to consensus. The consensus will still be reasonable. You know that you're going to get your timestamp from an honest node or times between two honest nodes, guaranteed, if less than a third are dishonest. All those guarantees apply, and so time dilation doesn't hurt us. Also, just for fun, Star Trek has the star date. which implies there's this global universal clock across the whole galaxy. Yeah, Einstein says that's impossible. You can't even talk about whether two events happened at the same time or different times if they happen in different solar systems moving with respect to each other. It's not that we don't know which one happened first. It isn't even a meaningful thing that one happened before the other. It's kind of mind-blowing, kind of hard to even grasp that there isn't a one universal clock for the world. But in Star Trek, they all just use the one universal clock for the world. I don't know how that works. But you could deploy Hashgraph across the galaxy and end up with a consensus timestamp on every event in every location. Basically generate our own universal clock, which would be kind of fun.
All right, for the fellow Trekkies out there, that is, anyone want to build that? We would love to see it. Okay, the next person is wondering whether Hedera's ABT guarantee is conditioned on the requirement that the list of nodes be known to all. When the network becomes permissionless, will it still be ABT?
Oh, yes, it will. We only have 4 minutes to cover this. Are we allowed to go later? Can we go more than 4 minutes?
We can go a couple minutes, but I think I believe I have a stop, and I think you do too.
Okay. In that case, yes, it is ABFT, even in this case. And the reason is, first of all, you don't technically have to know who the nodes are. You have to know how much stake everyone has. And remember, the whole point of a ledger is for everyone to know how much is in every account. So, every ledger knows, every node knows how many are in each account. That's kind of universal. That's sort of the bedrock of what a ledger is. It's how we come to agreement on that very thing. Of course, in a proof of stake system, you need to know how much stake everyone has. If you have that, you're done. But it is helpful in a gossip system to be able to know each other's IP addresses. And every gossip system does that. You end up gossiping the IP addresses, and these lists of IP addresses may be slightly out of date, might even be false if there's a malicious node, but you kind of work around that, and it's good enough. In Hedera, we go one step beyond that. We have a file system in Hedera where we actually store all the IP addresses. And so the list of the IPs itself is one of the pieces of information that the ledger itself has come to consensus on. And every time there's a change to it, the entire ledger reaches consensus on that time at which that change occurs. And if you ask for what's the contents of that file, you get the latest version of that file, and you can get cryptographic proof. The mirror nodes get cryptographic proof that what they think is that file actually is that file. And so we actually do have a universal knowledge of that. You could build a system without it. You could just have a gossip system where we gossip the IP addresses. But it's kind of cool eating our own dog food this way. The ledger itself remembers all the IP addresses. And then you could say, hey, what if a node drops off? Do we need to do something? Should we punish a node for dropping offline? And in a lot of ledgers, you don't know if a node drops offline. Maybe it's not doing any hashing, but how would you know it's not doing any hashing? You can't look inside of it and see. You don't even know if it's doing the right thing. And we gossip, but there's no record of the gossip, so you don't know if it stopped gossiping. In Hedera, though, we're using a hash graph, which is a complete history of how we've all talked to each other. If a node, every time a node talks, within a fraction of a second, every other node in the network gets to see that history and knows that it talked, that it synced with someone. And the hash graph itself shows you how active nodes are. And so if we wanted to, we could build into the ledger itself the ability to say, if a node hasn't been participating in the last second or the last hour or the last day or whatever, it will be automatically removed from the address book. And we can even do that. You can make that entirely automated because every single node knows the entire history of how we talk to each other, and every single node is running the same software that uses that history. And so that's kind of a powerful thing. And that piece of the story, you only get from Hashgraph. But the rest of the stuff I said, you can do it. And even if you didn't have a Hashgraph, you could get it to work. But I love this part of the story. We can automatically disenroll nodes when they are not active. And then if they ever become active again, what they could do is send us a transaction saying, hey, I'd like to be active. And maybe they have to pay a fee or something. And then you make them part of the network again. So that's how that works.
All right, Lehman, we have 1 more minute, so I'm going to squeeze one more in here. Could AI be supported or enhanced upon the use of or through the use of Hedera?
Yeah, so this is fascinating. My background was actually AI. My PhD was actually in AI stuff. I love AI stuff. It's really cool. So maybe. One big thing in machine learning is you need lots of data. So we have to manage these data sets. But if a malicious person can corrupt your data set, it causes real problems. You can end up with having an AI system that is racist or that just hates you, just you individually. And you would never know it, but it's because they corrupted the data set. And so there is use for maybe storing things about the provenance of the data set, and maybe important people sign it, and that is stored in a way that's visible to everybody, and we can all know for sure what it is. You could store the data set itself in the ledger, or you could just store hashes of it and metadata about it. Just like we think it is important to keep track of the provenance of food and drugs and diamonds and things, we could say it's important to keep track of the provenance of the training data for AI. And there's a lot of other things along this line. As we go to a world of IoT, we're going to have more AI doing things and learning things and sharing data. And I think ledgers can be involved in sort of the address book of how they find each other, the identity system for when IoT machines have identities, for authenticating the information, or at least agreeing that everyone has agreed on the information and we're all seeing the same information. All those different levels, I think that you see ledgers and Hedera being part of AI.
Awesome. Thank you, Lehman. All right, we are at the top of the hour. For anyone who had, friends who weren't able to listen, we will have this recorded and we will share it on our YouTube channel going forward. If you enjoyed this session, despite our technical challenges at the beginning, please do let us know. If you want to keep submitting more technical questions for the town halls, if we have a quorum of those questions, we'll keep doing some of these. And hopefully Twitter will continue to improve the reliability of Twitter Spaces, and and we will all get better with practice. So thank you, everyone. Have a great rest of your week. Thank you, Lehman, for taking the time. And we hope to be in touch with everyone soon.
Thanks. Thanks, everyone.
Have a good one. Bye-bye.